Two things are true about the mind at once. It insists that the world holds still long enough to be reasoned about, and reasoning, pushed far enough, keeps showing that the world will not sit still for it. Physicists have spent a century finding that a cat can be neither alive nor dead until someone looks. Philosophers have spent longer than that, discovering that a ship with every plank replaced raises a question no carpenter can answer. Over the next 2 hours, you will meet 100 small traps built by careful thinkers to catch confidence off guard, a trolley bearing down on 5 strangers, a brain floating in a jar of nutrient fluid, a donkey who starves between 2 identical piles of hay, a hotel with infinite rooms that is somehow always full and always has room for one more. Some of these puzzles will hand you a clean answer. Most will not, and that is the point. A thought experiment is not a trick question with a hidden solution. It is a small, sealed test chamber built to isolate exactly the intuition your everyday thinking never has to examine. Settle in. None of these need solving tonight, and the good ones do not get less strange with familiarity. They just get more precisely strange, which is its own kind of company for a long evening. A trolley is running out of control down a track, and 5 people are tied to the rails ahead, unable to move. You are standing at a lever, pull it, and the trolley switches to a side track, where it will kill 1 person instead of 5. Do you pull it? Philippa Foot posed a version of this scenario in 1967 while writing about abortion law, and Judith Jarvis Thomson sharpened it a few years later into the form most people now know. Nearly everyone who hears the lever version says pull it. 5 lives for 1 seems like simple arithmetic, but change one detail and the arithmetic stops feeling simple. Instead of a lever, imagine you are standing on a footbridge above the track, next to a large stranger. The only way to stop the trolley is to push him off the bridge, where his body will block it. Same math, 5 lives saved for 1 lost, and yet most people who would happily pull the lever refuse to push the man. Something in the mind treats those 2 acts as different, even though the ledger comes out identical. Philosophers call the divide between them the distinction between doing and allowing, or between an act and an omission, and it turns out to predict moral judgments about war, medicine, and law far better than any tally of outcomes does. Neuroscientists have since put people in brain scanners while they answer trolley questions, and the 2 versions light up different regions. The lever case recruits areas tied to calculation, the footbridge case recruits areas tied to emotion and physical harm. The debate has stopped being hypothetical too. Engineers writing the decision code for self-driving cars have had to write down, in actual software, what a car should do when a collision is unavoidable and someone has to be chosen. There is no version of the trolley problem that resolves cleanly, and that is exactly why it has survived 50 years of philosophy seminars and made its way into an engineering department. It does not test what you believe about numbers, it tests what you believe your own hands are allowed to do. A ship sails for so many years that, plank by plank, nail by nail, every single piece of the original hull is eventually replaced. The wood that carried it out of harbour on its first voyage no longer exists anywhere on the vessel. Is it still the same ship? The Greek biographer Plutarch recorded the puzzle almost 2,000 years ago, attaching it to the mythical ship of Theseus, supposedly preserved by the Athenians through continuous repair. Plutarch noted that some philosophers of his own time already treated it as a standing example in debates about identity, which means the question is older than any surviving text that poses it. The puzzle gets sharper with one addition. Suppose someone collects every discarded plank as it comes off the ship and board by board reassembles them into a second vessel, identical in shape to the first. Now there are 2 ships. One has all the original material and none of the continuous history. The other has all the continuous history and none of the original material. Only one of them can be the real ship of Theseus, if either is, and there is no experiment that settles which. The puzzle is not really about ships. It is about anything that persists by continuous replacement rather than by staying materially the same, which turns out to describe almost everything that is alive. The body renews its own tissue constantly, cell by cell, over the course of years, so that very little of the physical material present at one birthday is still present a decade later. A river is never the same water twice, yet it is still called the same river on every map. Company, a nation, a marriage, a self. Each one persists as a pattern held together through time, not as a fixed lump of matter carried unchanged from one day to the next. The ship of Theseus asks what identity is actually made of, if not the material. Philosophers have proposed answers involving form, function, and continuity of memory without ever converging on one. The ship is still out there in every version of the story, sailing under its old name, built of wood that has never once touched the water it first set sail on. In 1935, the physicist Erwin Schrödinger devised an experiment he never intended anyone to actually perform: seal a cat inside a box with a small amount of radioactive material, a Geiger counter, and a vial of poison rigged to break if the counter detects decay. The radioactive atom has a 50% chance of decaying within an hour, entirely governed by quantum mechanics, which describes such events not as unknown, but as genuinely undetermined until observed. According to the mathematics of quantum theory at the time, until someone opens the box and looks, the atom exists in a superposition of having decayed and not having decayed at once, and because the cat's fate is wired directly to that atom, the cat must be described as simultaneously alive and dead. Schrödinger built this scenario as an objection, not an endorsement. He wanted to show how absurd it becomes when the strange rules that clearly govern subatomic particles get scaled up to something as familiar as a cat, and he succeeded. The image has outlived nearly every technical detail of the physics that produced it. The actual debate the thought experiment triggered has never fully closed. One school, the Copenhagen interpretation, holds that observation itself collapses the superposition into one definite outcome, though nobody has ever agreed on what counts as an observation or why a measuring device would be exempt from the same quantum rules as everything else. Other physicists have proposed that the universe simply splits into two branches at the moment of decay, one where the cat lives and one where it does not, each equally real and simply unaware of the other. Still others argue that the wave function was never a description of physical reality in the first place, just a bookkeeping tool for predicting probabilities, in which case the cat was fine all along and the paradox was a category error. No experiment has ever forced a resolution, because the moment anyone builds a version of the box, the very act of building it collapses the puzzle before it starts. Physics can predict, with extraordinary precision, the odds that the atom decays in the first hour. It has never once told anyone what it is like to be the cat. How would you know right now that you are not a brain suspended in a vat of nutrient fluid, wired to a supercomputer that feeds you a perfectly convincing simulation of a body, a room, and a life? The philosopher Hilary Putnam posed the scenario in 1981, but the worry underneath it is centuries older. René Descartes ran a version of it in 1641, with an evil demon standing in for the supercomputer, deceiving the philosopher about the existence of his own hands. The unsettling part is not the science fiction imagery. It is that every piece of evidence you could possibly gather to disprove the scenario would itself be fed to you by the same vat. Look at your hands, and the vat shows you hands. Pinch yourself, and the vat delivers the exact sensation of a pinch. Ask a friend to confirm the world is real, and the vat supplies a friend who says yes. There is no test you can run from inside the system that the system could not also simulate the result of, which means the hypothesis is, in a strict sense, unfalsifiable from where you are standing. Putnam himself thought he had found a way out, arguing that the very words a brain in a vat would use to think the thought I am, a brain in a vat, would refer only to the simulated brains and vats inside its own simulation, never to the real ones outside it, so the sentence could never be truthfully asserted by the very mind that needed to assert it. Not every philosopher finds that argument satisfying, and the deeper question survives the objection. Either way, what actually distinguishes justified confidence in the ordinary world from a compelling illusion of one? The scenario resurfaces every time culture needs a fresh way to ask it. Most famously repackaged in 1999 as a red pill and a blue pill, the thought experiment does not claim you are being deceived. It only shows that whatever certainty you feel about the room around you right now was never built on proof. It was built on trust the vat has never once been asked to earn. Robert Nozick offered a strange trade in his 1974 book Anarchy, State, and Utopia. Imagine a machine that can give you any experience you want, indistinguishable from the real thing, for the rest of your life. Floating in a tank with electrodes attached to your brain, you could write the great novel, fall in love, win the championship, feel every triumph you have ever wanted, and never know it was not real. Would you plug in? Nozick was writing against a long tradition in philosophy called hedonism, which holds that pleasure, and only pleasure, is what ultimately matters to a good life. If hedonism were true, plugging in should be an easy decision. The machine offers unlimited pleasure at zero cost. And yet Nozick found, and later surveys of ordinary people have largely confirmed, that most people say no. Something about the machine's promise misses what they actually want. even though it delivers, by hypothesis, everything hedonism says they want. Nozick argued this reveals three things people quietly value that pleasure alone cannot supply. First, people want to actually do things, not merely have the experience of having done them. A simulated Olympic medal is not a medal, even if it feels exactly like winning one. Second, people want to be a certain kind of person, formed by real choices and real consequences, not a body floating in a tank being fed sensations. Third, people want contact with reality itself, not a limitlessly good substitute for it, because a substitute, however convincing, is still a substitute. Critics have pushed back for decades. Some argue the refusal is really just fear or unfamiliarity, that a generation raised on convincing simulations might answer differently. And modern versions of the question, that people who grew up with rich video games and virtual worlds have in fact found the refusal rate dropping. Others argue the thought experiment says less about pleasure than it does about how attached people are to the specific, messy, real world they already have, flaws included. The tank is still sitting there in every retelling of the puzzle, plugged in and waiting, offering the best life anyone could design. Almost everyone who is offered it still says no. In 1980, the philosopher John Searle asked readers to imagine a man locked in a room who does not speak a word of Chinese. He is given a large rulebook, written entirely in English, that tells him exactly which Chinese symbols to write back whenever he receives a card with Chinese symbols on it, purely by matching shapes according to the rules, with no understanding of what any of it means. From outside the room, people slide in questions written in Chinese and receive back coherent, fluent answers, also written in Chinese. To anyone outside, the room appears to understand Chinese perfectly. Inside, there is only a man shuffling symbols he cannot read according to a rulebook he can follow mechanically. Searle built the scenario to attack a claim then popular among artificial intelligence researchers, that a computer running the right program, one that could pass for a fluent Chinese speaker in every observable respect, would thereby actually understand Chinese, in the same sense a person does. Searle's argument is that the man in the room is functionally identical to such a computer, running the exact same kind of symbol manipulation, and the man in the room obviously does not understand a single word. Therefore, Searle concluded, no amount of pure symbol shuffling, however sophisticated, produces real understanding, only the appearance of it. Defenders of the original AI claim replied with what has become known as the systems reply. Perhaps the man himself does not understand Chinese, but the entire system, man plus rulebook plus room, does, in some emergent sense that does not require any single part of it to understand anything. Searle was unmoved, arguing that even if the man memorized the entire rulebook and did the whole task in his head, with no room and no external system left to point to, he still would not understand Chinese, and the intuition against it would remain exactly as strong. The debate never resolved, and it has only become more urgent since language-generating computer programs began producing fluent, convincing text on demand. Something is happening inside those systems that looks, from outside, exactly like understanding. Whether anything on the inside is actually understanding anything is the same question Searle's room asked more than 40 years ago, unanswered. Mary has spent her entire life in a room with no color in it. Every surface is painted in shades of black, white, and grey. She has never once seen the color red, and yet, through black and white books and a black and white television screen, she has learned absolutely everything there is to know, in a strictly physical sense, about the science of color. The exact wavelengths of light, the precise way the human eye's cone cells respond to them, the neural pathways that carry the signal to the visual cortex. Every physical fact about color vision is available to her, and she has mastered all of it. One day, Mary walks out of the room and sees a ripe red tomato for the first time. The philosopher Frank Jackson, who devised the scenario in 1982, asked a simple question: does Mary learn anything new at that moment? Almost everyone's intuition says yes. Obviously, she learns what red actually looks like, something no physical description, however complete, ever conveyed. If that intuition is correct, Jackson argued, it proves that physical facts alone cannot capture everything there is to know about conscious experience, because Mary had every physical fact and was still missing something until the moment she opened her eyes. Philosophers call the missing ingredient qualia, the raw felt quality of an experience, and the argument became one of the sharpest challenges to physicalism, the view that everything that exists, including the mind, is ultimately physical. Physicalist philosophers have pushed back in several ways. Some argue Mary does not gain new factual knowledge at all. only a new ability, the ability to recognize red when she sees it, which is compatible with physicalism because abilities are not facts about the world. Others argue that if Mary truly knew every physical fact, including the exact physical state her own brain would enter upon seeing red, she actually could deduce in advance exactly what the experience would be like, and her surprise upon seeing the tomato reveals only that no human could ever really hold that much information at once, not that anything non-physical was involved. Jackson himself later changed his mind and came to doubt his own argument. The tomato is still sitting there in every version of the story, exactly as red as it always was, waiting to be seen for the first time by someone who already knew everything about it except that. Send one twin on a rocket, traveling close to the speed of light to a distant star and back, while the other twin stays on Earth, and when the traveling twin returns, she will be measurably younger than the twin who stayed behind. This is not science fiction. It follows directly from Albert Einstein's special theory of relativity, published in 1905, which showed that time itself passes at different rates for observers, moving at different speeds relative to each other. The puzzle that earned the nickname the twin paradox is not really about whether this happens. It has been confirmed by real experiments, most famously in 1971, when physicists Joseph Afali and Richard Keating flew extremely precise atomic clocks around the world on commercial airliners, and found they ticked very slightly slower than identical clocks left on the ground, exactly matching relativity's prediction. The paradox is a logical wrinkle inside the theory itself. From the traveling twin's point of view, it is the earthbound twin who is moving away and back at high speed, so by the same logic, should not the stay-at-home twin be the younger one when they reunite? If both perspectives are equally valid, relativity seems to contradict itself, predicting that each twin should be younger than the other, which is impossible. The resolution turns on a detail easy to miss. The situation is not actually symmetric. The traveling twin has to accelerate, decelerate, turn around, and accelerate again to come home, while the stay-at-home twin experiences no such acceleration at all. That asymmetry breaks the tie, and careful calculation, accounting for the acceleration phases, shows definitively that the traveling twin ages less. The effect is vanishingly small at ordinary speeds, which is why nobody notices it in daily life, but it grows dramatic as speed approaches the speed of light, and it has real, practical consequences today. The satellites that run the global positioning system in every phone experience time at a very slightly different rate than clocks on the ground do, due to both their speed and the weaker gravity at orbital altitude. In their onboard clocks have to be corrected constantly for exactly this effect, or GPS coordinates would drift by miles within a single day. The twin paradox is not a paradox anymore, it is a correction factor built into an app in your pocket. What rules would you choose to govern a society if you did not know, in advance, whether you would be born rich or poor, healthy or disabled, in the majority or a persecuted minority? The philosopher John Rawls Ed posed exactly this question in his 1971 book, A Theory of Justice, asking readers to imagine designing the basic rules of society from behind what he called a veil of ignorance, a hypothetical position in which nobody knows their own eventual race, sex, class, talents, or even their personal values and life goals. Rawls called this the original position, and his central claim was startling in its simplicity. A rule chosen under total uncertainty about your own future place in the system is by definition a fair rule, because nobody could rig it in their own favor without risking that the rigged outcome lands on them instead. Rawls argued that rational people reasoning behind the veil would not gamble on a society that might make them destitute in exchange for a chance at being wealthy. Instead, they would favor a cautious strategy, choosing rules that protect the worst-off position as much as possible, since any of them might end up there. From this he derived two famous principles, that basic liberties should be equal for everyone, and that any social or economic inequality should only be permitted if it actually benefits the least advantaged members of society, not merely the most successful ones. The thought experiment reframes almost every hard political question into a single test. Would you accept this rule if you had no way of knowing which side of it you would land on? It is a deceptively for half a century, and it has been argued over for half a century. Critics on one side say the veil produces an overly cautious, risk-averse society that undervalues ambition and reward for effort. Critics on the other side say it does not go nearly far enough, that a truly impartial chooser would demand far more radical equality than Rawls's principles deliver. Both camps, notably, keep using Rawls's own framework to make their case. The veil never actually gets lifted in real life. Everyone making the rules always already knows exactly which side of them they are standing on, which is the whole reason Raw LZ thought it was worth imagining a room where, for once, nobody does. A hungry donkey stands exactly halfway between two piles of hay, identical in every measurable way, same size, same freshness, same distance. With no reason to prefer one pile over the other, the donkey cannot decide which way to walk, and so, according to the puzzle's grim logic, it stands frozen between two perfectly equal options until it starves to death. The scenario is popularly attributed to the medieval French philosopher Jean Baillot-Aidan, though he never actually wrote it in this exact form, and older versions of the same puzzle appear in Aristotle's writings centuries earlier, applied to a man rather than a donkey. The puzzle survives because it exposes a genuine crack in a common assumption about how choice works, that a rational agent always acts for a reason, choosing the option supported by the strongest justification. If two options are truly perfectly identical, there is no reason to prefer either one, which means a strictly reason-driven agent should, in theory, be paralyzed exactly like the donkey, with reason itself offering no way to break the tie. Real animals and real people do not behave this way, obviously, and philosophers have proposed several explanations for why. One is that no two options are ever actually perfectly identical in the real world. There is always some tiny asymmetry, a slightly closer pile, a slight preference for left over right, that breaks the symmetry before paralysis sets in. Another is that decision-making does not run purely on comparative reasoning at all. It runs partly on noise, small random fluctuations in a nervous system that eventually tip the balance one way. The same way a marble balanced on the exact peak of a hill will eventually roll to one side or the other from the tiniest imperceptible nudge, without needing any reason to prefer that side. This second explanation has aged well. Modern neuroscience has found genuinely random, stochastic processes inside real neurons, meaning indecision between equal options might get broken not by insight, but by something closer to noise settling a coin flip. The donkey never actually starves in any serious retelling of the story. It eventually just picks one pile, for no particular reason at all, the way most real choices between near-equal options actually seem to get made. Two prisoners are arrested and held in separate cells, unable to communicate with each other. Each is offered the same deal: betray your partner and testify against them, and you go free while they serve 10 years. Stay silent, and if your partner also stays silent, you both serve just 1 year. But if you stay silent while your partner betrays you, you take the 10 years and they walk. If both of you betray each other, you both serve 5 years. The dilemma, formalized in 1950 by the mathematicians Merrill Flood and Melvin Drescher, and popularized shortly after by Albert Tucker, produces a strange result once you actually work through the logic. No matter what your partner does, betraying them always gives you a better outcome than staying silent. If they stay silent, betraying beats staying silent, 1 year versus 0. If they betray you, betraying still beats staying silent, 5 years versus 10. Betrayal is what game theorists call a dominant strategy, mathematically the best move regardless of what the other player chooses. The catch is that this logic applies symmetrically to both prisoners, which means two perfectly rational players, each independently doing the smartest thing available to them, end up both betraying each other and both serving 5 years, a worse outcome for both of them than the 1 year each would have gotten by cooperating. Individual rationality produces a collectively irrational result. This is not just a puzzle about prisoners. The same structure appears whenever two parties would both benefit from cooperation, but each has an individual incentive to defect. Arms races between nations, price wars between competing businesses, overfishing shared waters, even the choice to litter in a public park. Real people, tested repeatedly in laboratory versions of the game, cooperate far more often than the cold logic predicts, especially when they expect to interact with the same partner again, which suggests that trust, reputation, and the shadow of future encounters do real work that a single isolated round of the dilemma cannot capture. The mathematics describes a trap. The behavior of actual humans, most of the time, is the story of finding a way partly out of it. An entity known for being an almost perfect predictor of human choices presents you with two boxes. Box A is transparent and contains $1,000, visible right now. Box B is opaque and it contains either $1 million or nothing, depending on a prediction the entity made about you before you ever arrived. If it predicted you would take only Box B, it filled Box B with $1 million. If it predicted you would take both boxes, it left Box B empty. You may choose to take only Box B, or both boxes, and the prediction has already been made and locked in, whatever it was. The physicist William Newcomb devised the puzzle, and the philosopher Robert Nozick brought it to wide attention in 1969, and it split decision theorists into two camps that have never fully reconciled. One camp reasons this way: whatever is in box B is already fixed, sitting there right now, unaffected by anything you decide in this moment, so you should simply take both boxes and collect whatever is in B plus the guaranteed 1,000 in A. This is called the dominance argument, and it feels airtight on paper. The other camp reasons differently. The whole premise is that the predictor is almost never wrong, which means people who take only box B overwhelmingly end up having been predicted correctly and walk away millionaires, while people who take both boxes overwhelmingly end up having been predicted correctly too, walking away with only the $1,000 because the entity foresaw their greed. If you take the track record seriously, taking only box B is by far the better bet, even though nothing you do now can retroactively change what has already been placed in the box. Both arguments are logically valid given their own assumptions, and each side considers the other's reasoning to be a kind of trap. The dispute exposed a real fracture inside decision theory itself, between what is called causal decision theory, which cares only about what your action causes, and evidential decision theory, which cares about what your action reveals about the kind of world you are in. Surveys of professional philosophers have found the split roughly persists among experts today, which is a strange thing to still be unresolved about a puzzle involving two cardboard boxes and free money. Step into a booth on Earth, and a machine scans your body down to the last atom, transmits that information to Mars, and reconstructs an exact atomic copy of you there, indistinguishable in every respect, memories and personality intact, while the original body on Earth is destroyed in the scanning process. Most people first encountered this exact device on a television screen, but the philosopher Derek Parfit built a rigorous version of the puzzle in his 1984 book, Reasons and Persons, using it to ask a harder question than science fiction usually bothers with. Is the person who steps out on Mars actually you, or is it a new person who merely believes correctly that they are you? The intuitive answer splits people almost evenly. One view holds that since the Mars arrival has all your memories, all your personality, every psychological trait you have, it simply is you continued, just relocated by an unusual method, no different in kind from falling asleep and waking up with a slightly altered brain state each night. The other view insists that the original you was destroyed on Earth, full stop, and what appears on Mars is a perfect copy, a different person having an identical experience to the one you would have had, which is cold comfort if you were the one about to step into the booth. Parfit sharpened the puzzle further by imagining a broken teleporter that fails to destroy the original body, leaving two people, one on Earth and one on Mars, both equally convinced they are the real you, both holding all your memories. If personal identity requires a single continuous thread, this scenario breaks it outright, since neither copy has any better claim to being the original than the other. Parfit's own conclusion was radical. He argued that the entire concept of personal identity as a fixed, single, unbroken thread through time is something of an illusion, that what actually matters is not identity in some strict metaphysical sense, but psychological continuity and connectedness, degrees of which can come in more than one copy at once without contradiction. The booth on Mars is still standing in every version of the thought experiment, and the person who steps out of it always insists, with total sincerity, that the trip felt like nothing at all. In Plato's Republic, the character Glaucon tells the story of a shepherd named YGs who discovers a ring that makes its wearer completely invisible whenever he turns the setting inward. YGs uses the ring to seduce the queen, murder the king, and take the throne for himself, entirely unseen and never held accountable for any of it. Glaucon poses the ring as a challenge to his teacher. If any person, however virtuous, were given this ring and could act with total impunity, guaranteed never to be caught, would they still choose to behave justly, or would the fear of consequences turn out to have been the only thing keeping them honest all along? It is one of the oldest thought experiments in Western philosophy, written down roughly 24 centuries ago, and it cuts straight at a question every system of law and morality eventually has to face. Is justice something people value for its own sake? Or is it only ever a strategy adopted because getting caught is expensive? Plato has Socrates argue, across the rest of the Republic, that a truly just person would refuse the ring's temptations, not out of fear, but because injustice corrupts the soul of the person who commits it regardless of whether anyone ever finds out. damaging their inner life in a way that no amount of stolen wealth or unearned power could repay. Modern psychology has since run its own quieter versions of the same test. Studies on anonymity consistently find that people behave measurably less honestly when they believe they cannot be observed or identified, from unattended honesty boxes to online anonymity effects. Evidence Glaucon would likely have found unsurprising rather than reassuring, but the studies so consistently find that most people do not behave as badly as they could, even under near-total anonymity, holding on to some of their ordinary standards even when nothing external would punish abandoning them. The ring has never actually been found. The question it was built to ask, whether goodness is a genuine trait or merely good behavior under supervision, gets a small, partial answer every time someone finds an unattended honesty box, a dropped wallet, or an empty room, and quietly does the harder thing anyway. Blaise Pascal, the 17th century mathematician who helped invent probability theory, applied his own subject to a question that seemed to sit entirely outside its reach: should a person believe in God? Pascal's argument set aside evidence and proof entirely, and instead treated belief as a bet, laid out with the same cold arithmetic he would use for any other wager. If God exists and you believe, you gain an infinite reward. If God exists and you do not believe, you risk an infinite loss. If God does not exist, the cost of having believed is comparatively small, some for gun pleasures, some Sunday mornings spent differently, while the cost of having disbelieved is also small. Laid out this way, believing dominates every other option. It produces either an infinite gain or a small loss, while disbelief produces either an infinite loss or a small gain, and infinity, multiplied by even a tiny probability of God's existence, still outweighs any finite calculation. Pascal wrote the wager not as a proof that God exists, but as a practical argument for why belief is the better bet even under total uncertainty. And he suggested that a person who found belief difficult should simply act as a believer acts, attend the rituals, live the practices, and let the habit eventually produce the genuine faith that reason alone had failed to supply. The wager has drawn sharp objections for centuries. One is the many gods problem. The argument works equally well or equally badly for any religion promising infinite reward, so it gives no actual reason to pick one faith over any of the thousands of other faiths making the identical promise, each cancelling the others out. Another objects that belief may not be something a person can simply choose to adopt for strategic reasons, the way one chooses a stock to invest in, since sincere belief seems to require actually being convinced, not merely finding it advantageous to act convinced. A third points out that an all-knowing God, if one exists, would presumably see through a wager-driven conversion and value it less than genuine conviction anyway, undermining the whole calculation from the inside. The wager still gets taught in philosophy courses, not because it settles anything about God, but because it is one of the cleanest illustrations ever written of how decision-making under radical uncertainty actually works, applied, almost by accident, to the largest question anyone has ever tried to run the numbers on. Take a single grain of sand. One grain is obviously not a heap. Add a second grain. 2 grains are still, just as obviously, not a heap. In fact, adding just 1 grain to any collection that is not a heap can never, on its own, turn it into a heap. A single grain is too small a difference to cross so significant a line. Repeat that step enough times, one harmless grain after another, and eventually you have 10,000 grains, unmistakably a heap by anyone's judgment, built entirely out of steps that each individually preserved the claim that no heap had yet formed. Something in that chain of reasoning has to be false, because the conclusion is absurd, and yet every single step in the chain looks completely sound on its own. The puzzle, called the Sorit's paradox after the Greek word for heap, was recorded by the philosopher Eubulides in the 4th century BCE, and its bite comes from vague language rather than from sand specifically. The exact same structure appears whenever a word describes a property with no sharp boundary: tall, old, rich, bald, warm. There is no single hair whose removal turns a full head of hair into baldness, and no single dollar whose addition turns a poor person rich. Yet nobody doubts that some people are clearly bald, and some are clearly not, that some people are clearly rich, and some are clearly not. Philosophers have proposed several ways out. One approach, called epistemicism, insists there really is a sharp cutoff, some exact number of grains that makes a heap. We simply can never know exactly where it falls, because the word heap was never precise enough for humans to have fixed a boundary consciously. Another approach, fuzzy logic, rejects the idea that heapness is all or nothing at all, treating it instead as a matter of degree, where a collection can be 0.6 heap the way a light can be dimmed to 60%, rather than only ever fully on or fully off. A third simply accepts that ordinary language was never built for the precision philosophers are demanding of it, and that vagueness is not a flaw to be fixed but a permanent, load-bearing feature of how words like heap actually function. Nobody has ever produced the missing grain that would settle the argument. The heap just keeps growing, one uncontroversial grain at a time, until it is undeniably there. The ancient Greek philosopher Zeno of Elea, working in the 5th century BCE, argued that the fastest runner in the world could never overtake a slower one who had been given even the smallest head start. And worse, that motion itself might be logically impossible. His most famous version pits the legendary runner Achilles against a tortoise given a modest lead. By the time Achilles reaches the point where the tortoise started, the tortoise has moved a little further ahead. By the time Achilles reaches that new point, the tortoise has again moved a little further, however slightly. This repeats forever. Every time Achilles arrives where the tortoise just was, the tortoise has already advanced again, so Achilles must cross an infinite number of ever-shrinking gaps before he can catch up, and Zeno argued that an infinite number of steps, however small each one is, can never be completed in a finite amount of time. And yet, obviously, in the real world, a fast runner catches a slow tortoise easily in minutes. Something in the logic has to be wrong, even though each individual step of the argument seems airtight. The resolution had to wait roughly 2,000 years for the development of calculus by Isaac Newton and Gottfried Leibniz in the 17th century, which showed rigorously that an infinite series of shrinking distances can sum to a perfectly finite total. Half plus a quarter plus an eighth plus a 16th, continued forever, adds up to exactly 1, not to infinity, because each term shrinks fast enough that the whole series converges. Zeno's paradox is not actually a fact about the world, in other words, it was a gap in the mathematics available to describe the world, a genuine limitation in how the ancient Greeks understood infinite sums, mistaken for a limitation in reality itself. Some philosophers still argue Zeno's puzzles have a residual bite even after calculus resolves the arithmetic, pointing out that calculus tells us the sums add up correctly without necessarily explaining how an object physically completes infinitely many subtasks in finite time. Distinction between mathematical description and physical process that some find still unsettled. Achilles has been catching the tortoise for 24 centuries now, every single time, in every retelling. The mathematics finally caught up with what anyone watching the race could already see. Suppose someone builds a working time machine, travels backward to a point before their own parent was born, and kills their own grandfather. If the grandfather dies before having children, one of the time traveler's own parents is never born, which means the time traveler themselves is never born, which means they could never have built the time machine, or traveled backward to commit the murder in the first place. The grandfather paradox, one of the oldest and sharpest objections to the very idea of backward time travel, shows up in physics and science fiction discussions alike because it exposes a genuine logical contradiction rather than a merely emotional or practical objection. The scenario requires an event to prevent its own cause, which classical logic simply does not allow. Physicists who take time travel seriously as a theoretical possibility, permitted in some solutions to Einstein's equations of general relativity involving structures called closed time-like curves, have proposed a few different ways the universe might avoid the contradiction rather than banning time travel outright. One proposal, developed by the Russian physicist Igor Novikov, is called the self-consistency principle. It holds that any event which would create a paradox simply cannot happen, not because some external force intervenes, but because the laws of physics themselves only permit self-consistent histories to exist in the first place, meaning a time traveler attempting the murder would always, for some mundane reason, fail. The gun jams, the traveler slips, someone knocks their arm at the last second, not through supernatural intervention, but through the ordinary chaos of events conspiring, every single time, toward the one outcome that does not erase the traveler's own existence. A second, more radical proposal borrows from the many worlds interpretation of quantum mechanics. The time traveler does kill the grandfather, but doing so simply splits reality into a new branch, one where the grandfather dies and a version of the traveler is never born in that branch, while the traveler's own original branch continues on, untouched, elsewhere. No physicist has ever actually built a device to test either idea, since nothing resembling a usable time machine has ever been constructed. The paradox remains purely theoretical, a stress test run entirely on paper, checking whether the universe's rules can survive contact with their own most literal violation. In 1867, the physicist James Clerk Maxwell imagined a tiny, intelligent creature stationed at a small door between two chambers of gas, both at the same temperature. The demon watches individual molecules approach the door and opens it selectively, fast-moving. Hot molecules are let through in one direction, slow-moving, cool molecules are let through in the other. Given enough time, the demon sorts the gas so that one chamber becomes noticeably hotter and the other noticeably colder, with no external energy input at all, seemingly for free. This should be impossible. The second law of thermodynamics, one of the most reliable and heavily tested laws in all of physics, states that entropy, roughly speaking the amount of disorder in a closed system, can never decrease on its own. Heat flows from hot to cold, never the other way around, without work being done. Maxwell's demon appeared to violate that law outright, using nothing but careful observation and door opening to extract order from disorder for free, and the puzzle sat as a genuine challenge to physicists for over a century. The resolution came from an unexpected direction: information theory. In 1961, physicist Rolf Landau showed that the demon cannot actually sort molecules for free, because the act of measuring each molecule's speed and remembering the result, even briefly, requires storing information and erasing that information later. To reset the demon's memory for the next molecule has an unavoidable minimum energy cost, now called Landauer's principle. Every bit of memory the demon erases releases a tiny amount of heat, and when physicists tallied up the full energy accounting, including the cost of the demon's own memory, the entropy of the entire system, demon included, never actually decreases. The second law survives intact. The demon was never a free lunch. It was quietly paying an energy bill the whole time, just in a currency, information, that nobody in 1867 had yet learned to price. The thought experiment ended up doing something almost nobody expects a 19th century physics puzzle to do. It helped found an entirely new field, connecting thermodynamics directly to the mathematics of information, decades before anyone had built a computer capable of demonstrating why the connection mattered. Imagine an intellect vast enough to know, at a single instant, the exact position and exact velocity of every particle in the universe, together with a complete grasp of every law of physics that governs how particles interact. The French mathematician Pierre-Simon Loup Plahs proposed exactly this hypothetical being in 1814, arguing that for such an intellect, nothing would remain uncertain. The future and the past alike would lie completely open before it, calculable in every detail. Because in a strictly deterministic universe, one where the same causes always produce the same effects, the present state of everything fixes the entire future, the way the layout of dominoes fixes exactly how they will fall once the first one tips. Plahs was not being fanciful for its own sake. He was drawing out the full implication of the physics of his own era, Newtonian mechanics, which described the universe as a vast, deterministic machine, every motion of every planet and particle governed by fixed, calculable laws. If that picture were completely true, then, in principle, though never in practice, the entire history of everything, from the formation of galaxies to the contents of tomorrow's newspaper, was already locked in from the beginning, spectator sport for anyone with the demon's impossible calculating power, since nothing genuinely new or undetermined would ever occur. The demon was never meant to exist. It was a device for testing exactly how much freedom, if any, a purely mechanical universe leaves for chance or genuine openness. The 20th century complicated the picture considerably. Quantum mechanics, developed in the 1920s, introduced a kind of fundamental unpredictability into physics that Loup Plahs could not have anticipated. At the smallest scales, certain outcomes, like exactly when a specific radioactive atom will decay, are not merely unknown, but appear to be genuinely undetermined until they happen, not hidden information waiting to be measured, but the absence of a definite answer at all. If quantum mechanics is right in this respect, Loup Plahs's demon could never actually calculate the future perfectly, even with unlimited knowledge and unlimited computing power, because the universe itself has not yet decided some of the answers. The debate over how deep that indeterminacy actually runs, whether it is a fundamental feature of reality or merely a limit on what any observer can ever measure, remains open. The demon has never once been built, and depending on which side of that debate turns out to be right, it may be a mathematical impossibility rather than merely a practical one. Is there any way, in principle, to tell whether the physical universe you are living in is a base reality or an extraordinarily detailed computer simulation being run by some future civilization? The philosopher Nick Bostrom formalized this question in a 2003 paper, not by simply asserting that we are living in a simulation, but by laying out a careful trilemma, three possibilities of which at least one, he argued, is very likely true. The first possibility is that civilizations essentially never reach the technological stage capable of running a convincingly detailed simulation of conscious minds, perhaps because they destroy themselves or stagnate before getting there. The second is that civilizations do reach that stage but choose, almost universally, not to run such simulations for ethical or other reasons. The third possibility is that if neither of the first two is true, meaning some civilizations do reach that stage and do choose to run such simulations, then given enough time and enough computing power, the simulated minds in those simulations would vastly outnumber the original, non-simulated minds that ever existed, since one civilization could plausibly run vast numbers of simulated worlds at once. If the third scenario holds, Bostrom argued, then any individual mind wondering about this question is statistically far more likely to be one of the many simulated minds than one of the comparatively rare original ones, purely by the numbers. The same way a person picked at random from a stadium is more likely to be sitting in the cheap seats than on the field, simply because there are so many more cheap seats. Bostrom was careful never to claim the third scenario is definitely true, only that at least one of the three has to be, and that the third is not obviously the least plausible of the three, once you take the argument seriously. Critics have pushed back on several fronts. Some doubt that consciousness could ever actually arise inside a simulation running on any physical substrate, no matter how sophisticated. Others doubt that the computing resources required to simulate an entire universe down to the level of conscious detail could ever exist even for an advanced civilization, since simulating physics in full detail may require more resources than the universe being simulated actually contains. No test has ever been proposed that would conclusively settle the question either way from inside the system being asked about, which is, on its own, exactly the kind of situation the argument predicted we would find ourselves in. In the late 19th century, the physicist Ludwig Boltzmann helped establish that heat and entropy are fundamentally statistical phenomena, the large-scale average behavior of enormous numbers of randomly moving particles. One strange consequence of treating the universe this way is that, given enough time and enough random motion, even a wildly improbable arrangement of particles will eventually occur somewhere, purely by chance, the same way an enormous number of coin flips will eventually, somewhere in the sequence, produce an absurdly long unbroken run of heads. Modern cosmologists, extending Boltzmann's statistical reasoning to the scale of the entire universe, have pointed out an uncomfortable implication. In an infinite or extremely long-lived universe, random thermal fluctuations should, purely by chance and given enough time, occasionally assemble a fully formed, momentarily self-aware brain out of randomly colliding particles in otherwise empty space, complete with false memories of a lifetime and a false impression of an orderly universe around it, before immediately dissolving back into disorder. Cosmologists call this hypothetical entity a Boltzmann brain, and the unsettling part of the argument is a matter of relative numbers. In a sufficiently old or large universe, the calculations suggest that randomly assembled Boltzmann brains, popping briefly into existence and then vanishing, would vastly outnumber brains like ours, produced through the ordinary, low-probability but non-random process of stars forming, planets forming, and billions of years of evolution. If that is true, any brain wondering whether it is a Boltzmann brain should statistically expect, on the numbers alone, that it probably is one, a brief random fluctuation with false memories of a whole life and a whole universe, rather than a real observer embedded in real cosmic history. Physicists generally treat this conclusion not as something to be believed, but as a warning sign, called the Boltzmann brain problem, that something must be wrong with the specific cosmological model that produces it, since a scientific theory that predicts most of its own observers should not trust their own memories has effectively predicted its own unreliability. Several proposed fixes to cosmology, involving how the universe's rate of expansion behaves over extremely long timescales, are partly motivated by trying to avoid this exact conclusion. Nobody has ever caught a Boltzmann brain in the act of assembling. The argument works entirely on probability, run over timescales so long that the word eventually barely still means anything close to what it means in ordinary conversation. Out of every human being who will ever live, from the first person to the very last, roughly what fraction of that total number do you think has already been born? The doomsday argument, developed independently by the astrophysicist Brandon Carter and later refined by the philosopher John Leasley, uses a piece of statistical reasoning called the Copernican principle, the idea that, absent any special reason to think otherwise, you should assume your own position in a sequence is a fairly typical, randomly selected one, rather than an unusually early or unusually late one. Apply that principle to your own position among all humans who will ever exist, and something uncomfortable follows. Current estimates suggest that somewhere around 100 billion humans have lived so far. If you assume you are a roughly random sample from the full set of humans who will ever exist, then it would be a genuine statistical surprise to find yourself among the very first 100 billion out of, say, a total of 100 trillion humans across all of history, the same way it would be surprising to reach into a bag believed to contain either 10 or 10,000 marbles and pull out marble number 7. Just as pulling out a low number should update your guess toward the bag containing fewer marbles overall, the argument suggests that finding yourself this early in human history should update your estimate of how many humans will ever exist downward, toward a total population not vastly larger than the number who have already lived, implying humanity is statistically more likely to end relatively soon, in cosmic terms, rather than continuing to spread through the galaxy for millions of years to come. The argument has drawn heavy criticism since it was first proposed. Some philosophers argue it wrongly treats your birth position as a random sample in the first place, when in fact you were never randomly selected from anything. You exist because of a specific, non-random chain of ancestry, and the whole statistical framework may not apply. Others point out that the argument's conclusion shifts dramatically depending on arbitrary choices about how the sample space is defined, a sign that something is unstable in the reasoning itself rather than something genuinely predictive about the future. No consensus has formed on whether the argument reveals a real constraint on humanity's future, or merely a clever misuse of probability. It remains one of the few thought experiments that claims to extract a forecast about the fate of the species from nothing but a single fact: the number of people born before you. Picture a hotel with infinitely many rooms, numbered 1, 2, 3 and onward without end, and every single room is occupied. A new guest arrives and asks for a room. An ordinary hotel would have to turn them away. The mathematician David Hilbert, in a 1924 lecture explaining the strange properties of infinity, proposed a solution. Simply ask every current guest to move from their room to the next room over, room 1 to room 2, room 2 to room 3, and so on for every guest forever. Every existing guest still has a room, and room number 1 is now empty, ready for the newcomer. The hotel, despite being completely full a moment ago, has made room for one more, without adding a single room or removing a single guest. Hilbert pushed the puzzle further. Suppose an infinitely long bus arrives, carrying infinitely many new guests, all wanting rooms in an already completely full hotel. The solution again seems impossible on its face, and again works perfectly. Ask every current guest to move to the room number that is exactly double their current room number, room 1 to room 2, room 2 to room 4, room 3 to room 6, and so on, which frees up every single odd-numbered room, of which there are infinitely many, for the infinitely many new arrivals. The hotel, again completely full both before and after, has absorbed an entire infinite busload of guests without running out of space. Hilbert built this thought experiment to make an abstract mathematical fact, developed rigorously a few decades earlier by the mathematician Georg Cantor, viscerally intuitive. Infinity does not behave like an ordinary large number. Adding 1 to infinity does not produce a bigger infinity. Infinity plus 1 is still the same size of infinity, and even infinity plus infinity is still the same size of that infinity. A set of results that felt so paradoxical when Cantor first proved them rigorously that some of his own contemporaries dismissed his work as nonsense, and one prominent mathematician of the era even called it a disease from which mathematics would eventually recover. Mathematics never did recover from it, because there was nothing to recover from. Cantor's transfinite numbers turned out to be entirely rigorous, and are now a standard, uncontroversial part of set theory taught in universities worldwide. The hotel is never actually full, in the ordinary sense of the word, no matter how many buses keep arriving. It only runs out of room the moment someone tries to add a single finite guest to an already infinite line waiting outside its doors. You are a contestant on a game show facing 3 closed doors. Behind one is a car, behind the other two are goats. You pick a door, say door number 1, and before it is opened, the host, who knows exactly what is behind every door, opens one of the other 2 doors, always revealing a goat, and then offers you the chance to switch your choice to the remaining unopened door instead of sticking with your original pick. Should you switch? The puzzle takes its name from Monty Hall, the longtime host of the television game show Let Us Make a Deal, and it became a nationwide controversy in 1990 after the columnist Marilyn Vos Savant answered it correctly in her magazine column, stating that switching doubles your odds of winning from 1 in 3 to 2 in 3. Thousands of readers, including, by some accounts, hundreds of mathematicians and academics with doctorates, wrote in insisting she was wrong, that with 2 doors left, the odds must simply be 50-50. Vos Sufficienty was right, and the reasoning, once seen correctly, is airtight rather than merely clever. Your original pick had exactly a 1 in 3 chance of hiding the car, and that never changes just because a door gets opened later. It still has only a 1 in 3 chance. That means there is a 2 in 3 chance the car is behind one of the other 2 doors combined, and once the host, who always knows where the car is and always reveals a goat, eliminates one of those 2 doors, the entire 2 in 3 probability that used to be spread across both of them collapses onto the single remaining door. Switching wins 2 times out of 3. Staying wins only 1 time out of 3. The confusion nearly everyone feels is not a failure of intelligence. It happens because human intuition treats the situation as if the host had opened a door at random, which would indeed leave the remaining odds at 50-50, but the host's choice was never random at all, since the host always specifically avoids revealing the car, and that extra piece of non-random information is exactly what shifts the odds. The puzzle has since become one of the most widely used teaching examples in introductory probability courses precisely because it demonstrates, more vividly than almost any other example, how a single hidden assumption about randomness can quietly flip an entire calculation upside down. You are handed 2 identical envelopes and told that one contains exactly twice as much money as the other, though you have no idea which is which. You pick one at random and, before opening it, are offered the chance to switch to the other envelope instead. Should you switch? A tempting piece of reasoning says yes, always switch, and the reasoning looks convincing at first. Call the amount in your envelope X. There is a 50% chance the other envelope contains twice as much, 2x, and a 50% chance it contains half as much, half of x. The expected value of switching, averaging those 2 possibilities, works out to 1.25 times x, which is more than x itself, suggesting switching is always the better move. But this creates an absurd result, because the exact same argument applies symmetrically to the other envelope too. Whichever envelope you are currently holding, the reasoning says the other one has a higher expected value, which would mean you should switch back and forth forever, gaining value each time, which is obviously impossible since one of the 2 envelopes has a fixed, larger amount of actual money sitting inside it right now, unaffected by which one you happen to be holding. Something in the calculation has to be wrong, and pinpointing exactly what took mathematicians and philosophers considerably longer to agree on than the puzzle's playful setup would suggest. The core problem is a subtle error in how the expected value calculation treats the variable x. Labeling the amount in your current envelope as x, and then treating the other envelope as either 2x or half x, each with even odds, secretly assumes something about the underlying probability distribution of how much money could possibly be in either envelope that is almost never actually true, and once you fix an actual, specific pair of amounts, say $10 and $20, sitting in the 2 envelopes before you ever pick one, the seemingly ironclad 1.25 multiply argument collapses immediately. Switching from 10 to 20 is a gain, switching from 20 to 10 is a loss, and averaged over both cases, there is no advantage to switching at all. The puzzle survives in classrooms, not because the correct math is exotic, but because the flawed argument is so smooth and so persuasive that spotting the exact place where it goes wrong takes real, careful attention, which is precisely the skill the puzzle was built to test. On Sunday, a volunteer is put to sleep and told the full rules of an experiment she is about to take part in. A fair coin will be flipped. If it lands heads, she will be woken once, on Monday, and asked what she believes the probability is that the coin landed heads, then put back to sleep with no memory of the waking. If it lands tails, she will be woken on Monday, asked the same question, put back to sleep with her memory of that waking erased, and then woken again on Tuesday and asked the exact same question a second time. From her perspective, every waking is completely indistinguishable from every other. She has no way to tell, in the moment she is asked, whether it is Monday or Tuesday, or how many times she has already been woken before. What probability should she state, whenever she is asked, that the coin landed heads? The puzzle, formalized by the philosopher Adam E. Elgar in 2000, though built on earlier work, has produced one of the more stubborn ongoing disagreements in modern philosophy of probability. One camp, called halfers, argues that since the coin itself is fair, and nothing about the flip changes based on how many times she gets woken up afterward, the correct answer is simply 1/2, exactly as it was before she ever went to sleep. Being woken up provides her with no actual new information about which way the coin landed. The other camp, called thirders, argues that from her own perspective inside the experiment, at any given waking, there are 3 equally likely situations she could currently be in. It is Monday, and the coin was heads. It is Monday, and the coin was tails. Or it is Tuesday, and the coin was tails. And since 2 of those 3 situations correspond to a tails result, she should state a 1/3 probability of heads, not 1/2, because tails produces twice as many wakings as heads does, and she has no way of knowing which waking she is currently living through. Both camps can produce internally consistent mathematical frameworks supporting their answer, and professional philosophers of probability remains split on which framework correctly describes what a rational agent should believe when the very act of counting your own observations is entangled with the outcome you are trying to estimate. The volunteer has been given the exact same rules and asked the exact same question hundreds of times in academic papers over the past 2 decades, and no version of the answer has managed to put the argument to sleep. Which is better, a world with 10 billion people, each living a life of deep, rich flourishing, or a world with 10 trillion people, each living a life barely worth living, only slightly better than not existing at all, but multiplied across such an enormous population that the total sum of well-being, added up across every single person, comes out higher than in the smaller flourishing world. The philosopher Derek Parfit posed this comparison in his 1984 book, Reasons and Persons, working within a branch of ethics called population ethics, which tries to reason carefully about moral questions involving how many people should exist, and under what conditions, questions that classical ethical theories were rarely built to handle. Parfit was testing a natural-seeming principle called total utilitarianism, the view that the morally best outcome is whichever one maximizes the total sum of well-being across every person who exists added together, rather than the average well-being per person. Total utilitarianism has real appeal. It explains straightforwardly why bringing a new, happy person into existence is usually a good thing, and why a world with more flourishing people is generally better than a world with fewer. But Parfit showed that pushed to its logical extreme, the same principle forces you to accept that a vastly larger population of people whose lives are barely worth living is morally superior to a much smaller population living in genuine abundance and flourishing, as long as the sheer number of barely adequate lives is large enough to push the total sum higher. Parfit called this the repugnant conclusion, precisely because nearly everyone's moral intuition recoils from it immediately, even while finding it difficult to identify exactly which premise in the argument to reject. Reject total utilitarianism's simple additive logic, and you run into other problems just as troubling: average utilitarianism, which instead maximizes average well-being per person rather than the sum, ends up implying that it can be morally good to prevent happy people from ever being born, if their existence would slightly lower the population's average happiness, which strikes most people as its own kind of repugnant conclusion in reverse. Decades of work in population ethics since Parfit have proposed dozens of alternative principles, each one built specifically to dodge the repugnant conclusion, and each one so far has been shown to produce some other conclusion that feels just as difficult to accept. No framework has yet been found that avoids all of the traps at once. Imagine a creature that experiences pleasure with such extraordinary efficiency that it gains vastly more well-being from any given resource than an ordinary person ever could. Say 1,000 times more happiness from eating a sandwich than a human being would get from the same sandwich. The philosopher Robert Nozick introduced this creature, which he called a utility monster, in 1974 as a direct challenge to utilitarianism. The ethical theory that holds the morally right action is whichever one produces the greatest total sum of happiness or well-being across everyone affected. If the utility monster is real and its efficiency at converting resources into happiness is great enough, strict utilitarian logic leads to an outcome most people find monstrous in the ordinary sense of the word too. Society should funnel as many resources as possible toward the monster, even at the expense of everyone else's basic needs, because every sandwich redirected to the monster produces more total happiness in the world than that same sandwich would have produced by feeding an ordinary hungry person instead. And utilitarianism, taken purely at face value, cares only about maximizing the total sum, not about how fairly that sum gets distributed among the people involved. Nozick was not claiming such a creature actually exists. He was using it to expose what he saw as a structural weakness in pure utilitarian reasoning, namely that a theory focused entirely on maximizing an aggregate total has no internal safeguard against wildly unequal distributions, as long as the total keeps climbing. Defenders of utilitarianism have offered a few responses over the decades. Some argue that a genuine utility monster is almost certainly impossible in any real physical or psychological sense, since diminishing returns on pleasure, the pattern where each additional unit of a good thing brings progressively smaller gains in satisfaction, appear to be a nearly universal feature of real minds, which would make an unlimited efficiency pleasure machine biologically implausible rather than merely rare. Others have proposed modified versions of utilitarianism that build in explicit protections for fairness or for a baseline standard of well-being that cannot be sacrificed no matter how much aggregate utility is on offer elsewhere, essentially patching the theory to rule the monster out by design rather than by luck. The thought experiment has outlived the specific theory it was built to attack, because the underlying worry that maximizing a total can quietly justify grotesque unfairness in how that total gets divided shows up again in economics, public policy, and any system that measures success purely by an aggregate number. Consider the ordinary scientific claim that all ravens are black. Logicians recognize that this statement is logically equivalent to its contrapositive. Anything that is not black is not a raven. Both statements say exactly the same thing about the world, just phrased in mirror image form, and in formal logic, evidence that confirms one of two logically equivalent statements must also confirm the other, since they are, strictly speaking, the identical claim wearing different clothes. The philosopher Carl Hempel pointed out, in the 1940s, where this leads. If you walk outside and observe a black raven, that clearly counts as evidence supporting the claim that all ravens are black, no controversy there. But by the logical equivalence, observing anything that is not black and confirming that it is also not a raven should count, with equal logical force, as evidence supporting the exact same claim. A red apple is not black and it is not a raven either, so strictly by the logic, spotting a red apple in your kitchen technically confirms the hypothesis that all ravens are black, exactly as validly as spotting an actual black raven does. This feels absurd on its face, and Hempel intended it to feel absurd. He built the paradox specifically to expose a mismatch between the formal logic of confirmation, which is airtight, and the intuitive, everyday sense of what actually counts as relevant evidence for a claim, which strongly resists treating a red apple as raven-related evidence of any kind. Several resolutions have been proposed. One response argues the red apple genuinely is a tiny, almost imperceptibly small piece of confirming evidence, just so small in practical terms compared to observing an actual raven that human intuition simply rounds it down to zero, when a more careful statistical accounting would show it is not literally zero, only negligible. Another response points out that the actual number of things that are not black vastly outnumbers the actual number of ravens in existence, so each individual non-black, non-raven observation genuinely does confirm the hypothesis small, that no human observer could ever notice the difference across an entire lifetime of casual apple sightings, even though the formal logic keeps the confirmation technically real. The paradox never claims ravens are secretly not black, or that logic itself is broken. It claims something narrower and stranger, that the everyday concept of evidence and the formal logic of confirmation, which almost always point in the same direction, occasionally diverge just enough to make a red apple, of all things, a piece of ornithological data. Consider the sentence. This statement is false. If the sentence is true, then what it says must be the case, which means the statement really is false, contradicting the assumption that it was true. But if the sentence is false, then what it says is not the case, which means the statement is not false, meaning it must be true, contradicting the assumption that it was false. The sentence cannot consistently be true, and it cannot consistently be false either, which makes it a genuine logical paradox rather than merely a confusing or badly worded claim. Versions of this puzzle go back at least to the ancient Greek philosopher Eubulides in the 4th century BCE, and an earlier variant, attributed to the semi-legendary Cretan philosopher Epimenides, has a Cretan declaring that all Cretans are always liars, producing a similar self-undermining loop. The liar's paradox looks, at first glance, like wordplay, the kind of riddle meant to entertain rather than to threaten anything serious. It turned out to be far more consequential than that. In the early 20th century, mathematicians and logicians working to build airtight, gap-free foundations for all of mathematics ran directly into structurally identical self-reference problems. Bertrand Russell discovered a set-theoretic version in 1901, and in 1931 the logician Kurt Gödel used a carefully engineered self-referential sentence, one that effectively says of itself, "This statement cannot be proven within this system," to prove his incompleteness theorems, showing that any sufficiently powerful consistent mathematical system must contain true statements that the system itself can never prove. A result that permanently reshaped what mathematicians could ever hope to achieve. The liar's paradox, in other words, was not an isolated curiosity confined to clever sentences about lying. It was an early sighting of a structural feature buried deep inside any formal system capable of referring to its own statements, one that resurfaces in mathematics, computer science, and the theory of computation whenever a system becomes powerful enough to talk about itself. Logicians have proposed several technical ways to diffuse the paradox for practical purposes, mostly by restricting which sentences a formal system is allowed to construct in the first place, banning certain forms of direct self-reference before they can cause trouble. None of these fixes make the underlying puzzle vanish from ordinary language, where nothing stops anyone from simply saying the sentence out loud. It sits there, 24 centuries old, still perfectly capable of being neither true nor false the moment anyone actually says it. In a certain village, there is exactly one barber, and the villagers have agreed on a strict rule. The barber shaves every man in the village who does not shave himself, and the barber shaves no man who does shave himself. The question is simple enough to state and impossible to answer consistently. Who shaves the barber? If the barber shaves himself, then by the village's own rule, he belongs to the group of men who shave themselves, which means by that same rule the barber does not shave him, a direct contradiction. If the barber does not shave himself, then he belongs to the group of men who do not shave themselves, which means, by the rule, the barber does shave him, again a direct contradiction. Either answer breaks the very rule that was supposed to define the barber's job in the first place. Bertrand Russell devised this folksy version of the puzzle to illustrate, in plain language, a much more serious contradiction he had discovered in 1901 while working on the mathematical foundations of set theory. Russell had found that you could define, in formal mathematical terms, the set of all sets that do not contain themselves as members, and then ask, exactly as with the barber, whether that set contains itself. If it does, then by its own defining rule it should not. If it does not, then by that same rule it should. The contradiction, now called Russell's paradox, struck at the heart of a mathematical framework developed by the logician Gottlob Frege, that mathematicians of the era had hoped would provide an unshakable, fully rigorous foundation for the entirety of mathematics. Frege received Russell's letter describing the paradox just as the second volume of his life's work was going to print, and he added a stunned postscript acknowledging that his entire system had just been shown to be inconsistent. The barber never actually needs an answer in real life, because no such village, with such a rigidly self-referential rule, could ever actually exist. The paradox lives entirely in the space of things that can be described in language or notation, but cannot coherently exist. Mathematicians eventually rebuilt set theory on more careful foundations specifically designed to block this kind of self-reference from arising, a repair job that took decades and reshaped the entire discipline. The barbershop in the story was never real, but the crack it exposed in the foundations of mathematics very much was, and patching it remains one of the quieter, more consequential repairs in the history of the field. Suppose everyone in a village has a small box, and everyone calls whatever is inside their own box a beetle. No one is ever allowed to look inside anyone else's box, only their own, and the word beetle in this village refers to whatever each person finds when they look inside theirs. The philosopher Ludwig Wittgenstein posed this scenario in his 1953 work Philosophical Investigations, and he pointed out something strange about it. It is entirely possible that the contents of these boxes constantly change, or that some boxes are even empty, and the word beetle would still function perfectly well in the village's language, since nobody's private box is ever compared against anyone else's, and the word only ever gets used in public conversation, where all that matters is that everyone says beetle when talking about their box, regardless of what, if anything, is actually inside it. V.I.T. Gunstein built this scenario as an argument against a common assumption about how words for inner, private experiences, like pain or the felt quality of seeing red, actually work. It is tempting to think that when you say I am in pain, the word pain functions by pointing directly at some private inner sensation, only you have access to, in the same way beetle seems to point at the private, unshared contents of each person's sealed box. But V.T. Gunstein argued that if the inner thing really were entirely private and uncheckable, the way the box contents are uncheckable by anyone but the owner, then that private thing could play no actual role in how the word functions in the shared language everyone actually uses to talk to each other, since nobody could ever confirm whether their own beetle matches anyone else's, or even whether the word is being used consistently across different speakers at all. What actually gives a word like pain its meaning, V.T. Gunstein argued, is not some hidden private object it supposedly labels, but the public, observable behavior and shared circumstances surrounding its use, the wincing, the wound, the description offered to a doctor, all of which are things other people can actually witness and respond to. This argument, sometimes called the private language argument, became one of the most influential and most fiercely debated moves in 20th century philosophy of mind, because it strikes directly at the intuitive picture almost everyone carries of their own inner life as a private theatre only they can watch. Nobody in the village has ever compared beetles. The word gets used every single day regardless, doing all the work language needs it to do without ever once being checked against the thing it supposedly names. Imagine a creature physically identical to you in every conceivable respect, atom for atom, down to the exact same brain structure and the exact same neural firing patterns, behaving exactly as you would in every situation, laughing at the same jokes, wincing at the same pain, saying I am conscious in the same tone of voice you would use. The only difference is that this creature has no inner experience whatsoever. There is nothing it is like to be this creature, no felt quality to its laughter or its wincing, even though from the outside, including under any scientific instrument ever devised, it is completely indistinguishable from a genuinely conscious person. Philosophers call this hypothetical being a philosophical zombie, and the contemporary philosophers, David Chalmers, built the most influential modern version of the argument in the 1990s as part of what he termed the hard problem of consciousness, the puzzle of explaining why physical processes in the brain are accompanied by subjective experience at all, rather than occurring in total experiential darkness, the way the zombie's identical processes supposedly do. Chalmers' argument runs roughly like this. If a philosophical zombie is even conceivable, meaning it does not involve any actual logical contradiction to imagine one, even if no such creature could ever really exist given the actual laws of nature, then consciousness cannot be reducible to purely physical facts about brain structure and behavior, because two beings can share every single physical fact in common, while differing in exactly the one respect, inner experience, that matters most. If consciousness were nothing more than a particular pattern of physical activity, the zombie's identical physical activity should guarantee identical consciousness too, and the fact that we can coherently imagine otherwise suggests something about consciousness escapes purely physical description. Physicalist philosophers have pushed back hard on the very first step of the argument, arguing that the zombie only seems conceivable because our imagination is not actually tracking all the physical facts closely enough. Once you really and fully specify every physical detail of a functioning human brain, they argue consciousness is not an extra ingredient layered on top. It simply is that physical activity, described from a different angle. Chalmers and his allies respond that this move begs the very question at issue, assuming physicalism is true, in order to prove that the zombie's conceivability is illusory. Nobody has ever met a philosophical zombie, and by the argument's own design, nobody ever could tell if they had. Lightning strikes a swamp and, purely by an almost inconceivably improbable chance rearrangement of molecules, assembles a being that is, atom for atom, a perfect physical duplicate of a philosopher named Donald Davidson, who happened to be standing near that exact spot moments before being vaporized by the same strike. This new being, which philosophers have nicknamed Swampman, walks out of the swamp, greets David's son's friends by name, writes philosophy papers indistinguishable from David's son's own, and behaves in every observable way exactly as David's son would have. David's son himself introduced this scenario in 1987, not to speculate about lightning, but to ask a sharp question about meaning and reference. Does Swampman's use of words actually mean anything, in the way a normal person's words do, or is it empty mimicry that merely looks identical to meaning from the outside? David's son's own answer was that Swampman's words do not actually refer to anything at all, at least not right away, because meaning, on his view, depends on a causal history, a chain of actual past experiences, actual past encounters with the things being talked about, that connects a word to what it names. When Swampman says the word river, thinking of a specific childhood memory of a specific river, that memory-shaped thought has no real childhood behind it. No real river was ever actually experienced by Swampman, only by the original David's son who no longer exists. Swampman's utterance sounds identical, functions identically in conversation, and yet, on this view, is empty where the original was full. A perfect copy missing the one thing that supposedly made the original meaningful in the first place. Other philosophers have pushed back hard on this conclusion, arguing that meaning cannot possibly depend on an actual causal history in this stricter sense, since it would imply that Swampman, despite being functionally, behaviorally, and physically identical to a person with genuine thoughts, memories, and understanding, would nonetheless have none of these things, simply because of an accident in how he came to exist, a conclusion many find deeply counterintuitive on its own terms. The disagreement cuts to the heart of a genuine split in philosophy of language and mind, between views that ground meaning in a thing's causal history and views that ground it purely in a thing's current internal structure and behavior. Swampman has never actually walked out of any real swamp. The question of whether his words would mean anything if he did remains exactly as unresolved as it was the day David's son first proposed it. In Ursula K. Le Guin's short story The Ones Who Walk Away from Omelas, published in 1973, a city exists in a state of near-perfect happiness. Its citizens are healthy, its festivals joyous, its people free of guilt, envy, and violence, living lives of genuine, unforced flourishing. The story reveals, midway through, the price of all of it. In a locked basement room somewhere in the city, a single child is kept in filth and darkness and suffering, permanently, and every single citizen of Omelas knows this child exists, is being told exactly why, and understands, as an accepted foundational fact of their entire society, that the city's happiness depends directly and irrevocably on that one child's continued misery, that freeing the child would collapse the prosperity of everyone else. Nearly all the citizens, upon learning this as children themselves, eventually make peace with it and continue living their happy lives, having decided, in Le Guin's words, that the terrible justice of reality is to be accepted. A small number of citizens, on learning the truth, instead simply walk away from Omelas, alone into the unknown, refusing to participate in the arrangement any further, though the story never tells us where they go or whether life outside is any better. Le Guin did not build the story primarily as a plot to be resolved. She built it as a direct provocation aimed at utilitarian moral reasoning, the framework that judges the rightness of an action or an arrangement by whether it maximizes overall happiness, and she constructed Omelas specifically so that the arithmetic of total happiness comes out overwhelmingly favorable, a vast city of flourishing weighed against a single suffering child, forcing the reader to ask whether that lopsided ratio actually settles the moral question, or whether some suffering is simply too specific, too deliberate, and too foundational to be redeemed by any amount of aggregate happiness stacked against it. The thought experiment deliberately withholds an easy resolution. Le Guin never tells the reader that walking away is right, only that some people do it, and the story has been used ever since, in philosophy classrooms and beyond, as a test case for anyone confident that a sufficiently large sum of well-being can justify a localized cost. Every version of this story ends the same way. The city keeps functioning exactly as it did before, its festivals continuing, its child still locked in the same, whether or not anyone in a given retelling decides to walk. Imagine recruiting the entire population of a very large country and giving each person a very simple job. Represent one neuron. Each person is connected to a handful of others by radio, following simple rules about when to signal the people they are connected to, mimicking, in aggregate, the exact pattern of neural connections and firing rules found in an actual human brain, scaled up to more than 1 billion participants instead of roughly 86 billion neurons. The philosopher Ned Block proposed this scenario in 1978, sometimes called the China brain or the Chinese nation thought experiment, as a direct challenge to functionalism, an influential theory in philosophy of mind, holding that mental states are defined entirely by their functional role, meaning what causes them and what effects they produce, rather than by what physical material they happen to be made of. If functionalism is correct, then any system that implements the same functional organization as a conscious brain, following the same input-output patterns regardless of the underlying material, should itself be conscious, whether that material is neurons made of biological tissue or 1 billion people relaying radio signals to each other, according to a rulebook. Block's argument leans hard on intuition. It seems deeply implausible, almost absurd, that a country's population, organized this way, would thereby generate a single unified conscious mind experiencing anything at all, hovering somehow above and beyond the billion individual, ordinarily conscious people doing the relaying, even though the system as a whole is, by hypothesis, functionally identical to a working brain. If the intuition is right, and no such system-level consciousness ever emerges no matter how perfectly the functional organization is replicated, then functionalism has to be missing something, some additional requirement beyond mere functional organization, that a system needs before it counts as truly conscious, perhaps something specifically to do with the biological material the organization is implemented in. Defenders of functionalism have replied that the intuition itself may simply be a failure of imagination rather than a genuine insight, arguing that human minds are simply bad at intuitively grasping what a billion-person, radio-linked system would actually be like from any perspective, and that dismissing its consciousness purely because the scenario feels strange is not a rigorous argument, just an appeal to how unfamiliar it sounds. The debate remains unresolved, sitting at the center of one of the harder open questions in philosophy of mind, whether consciousness is a matter of pattern and organization alone, or whether it also requires some specific kind of physical stuff to run on. A teacher announces on Monday that a surprise exam will be given exactly once during the following week, Monday through Friday, and that the students will have no way of knowing in advance which day it will fall on until the morning it actually happens. A clever student works through the implications and reasons her way into a strange conclusion. The exam cannot be on Friday, she reasons, because if it had not happened by Thursday evening, every student would know with certainty that it must be Friday, which would make it entirely predictable, not a surprise at all, violating the teacher's own announcement. Having ruled out Friday, she reasons the exam also cannot be on Thursday, because if it had not happened by Wednesday evening, and Friday has already been ruled out, the students would know for certain it must be Thursday, again removing the surprise. By the same logic, she eliminates Wednesday, then Tuesday, then finally Monday, concluding that no day at all is possible for a genuinely surprising exam, since every single day, once you reason through the elimination carefully enough, becomes predictable given the days already ruled out before it, and yet, when the teacher gives the exam on, say, Wednesday, the students are, in fact, completely surprised, exactly as promised, having convinced themselves through what seemed like airtight logic that it could not happen on any day whatsoever. Something has clearly gone wrong in the reasoning, since the exam plainly can and does happen as a real surprise in practice, but logicians have argued for decades over exactly where the flaw lies, and no single diagnosis has won universal agreement. One line of analysis argues that the student's elimination argument secretly assumes she can trust her own future reasoning process completely, when in fact the very act of reasoning her way to a conclusion on Sunday night changes what would count as a surprise on any later day, meaning the argument undermines its own premises partway through rather than reaching a stable conclusion. Another line of analysis, drawing on the same territory as self-referential logical puzzles like the liar's paradox, argues that the phrase surprise exam is subtly self-referential in a way that makes the teacher's original announcement genuinely difficult to state without contradiction, closer to a logical trap embedded in language than a simple scheduling problem. The exam always happens exactly once, on exactly one ordinary day of the week. The paradox has never once managed to actually prevent a single teacher from giving one. Sometime around 1950, over lunch with colleagues at Los Alamos, the physicist Enrico Fermi reportedly interrupted a casual conversation about extraterrestrial life with a single blunt question: where is everybody? Fermi's point, later developed into a full argument, was not that alien life is impossible, but that the universe's sheer size and age make its apparent silence deeply strange. The observable universe contains hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them older than our own sun by billions of years. Plenty of time, by any reasonable estimate, for at least some civilizations among that vast number to have developed spaceflight and begun spreading outward. Even at travel speeds far slower than light, calculations suggest a single expanding civilization could plausibly colonize an entire galaxy within a few tens of millions of years, a blink of an eye set against the roughly 13 billion year age of the universe. Given that much time and that much opportunity, Fermi's puzzle asks, why has nobody visited, radioed, or left any detectable trace anywhere we have looked? The gap between the seemingly high probability of advanced alien civilizations existing and the total absence of any confirmed evidence for them is what is now called the Fermi paradox. In 1961, the astronomer Frank Drake formalized the underlying probability estimate into what is now called the D-Rake equation, a chain of multiplied factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, and several more, each highly uncertain, meant to estimate how many detectable civilizations might currently exist in the galaxy. Proposed explanations for the silence range widely in both plausibility and comfort. Some suggest that complex intelligent life is simply far rarer than the equation's optimistic estimates assume, that we may be genuinely alone or nearly so. Others suggest civilizations reliably self-destruct, through war, environmental collapse, or runaway technology, before they ever manage to spread beyond their home planet, a possibility researchers have grimly nicknamed the Great Filter. Still others suggest civilizations exist in great numbers, but deliberately avoid contact, or that our search methods and technology are simply too limited or too recent to have detected signals that are out there. No evidence has settled the question in either direction. The paradox is not a discovery about aliens at all. Strictly speaking, it is a discovery about how uncomfortable a very large, very old, and very quiet universe actually is once you do the arithmetic honestly. In the early 1980s, the political scientist Robert A.K. Joulrod ran a series of tournaments testing a variation on the classic prisoner's dilemma, one designed to feel much closer to real life. Instead of playing the game just once against a stranger you will never meet again, participants played hundreds of rounds against the same opponent, remembering every previous round and adjusting their strategy accordingly. A.K. Joulrod invited game theorists from around the world to submit computer programs, each one encoding a strategy for deciding, round by round, whether to cooperate with the opponent or betray them, and then ran every submitted strategy against every other strategy repeatedly in a round-robin tournament to see which approach accumulated the most points overall. The winner, submitted by the mathematician Anatole Rappaport, was strikingly simple, especially compared to some of the far more elaborate, deceptive strategies submitted by other competitors. Called tit for tat, it followed just two rules: cooperate on the very first round with any new opponent, and after that, simply copy whatever the opponent did on the previous round. Cooperating if they cooperated, retaliating with one round of betrayal if they betrayed, then immediately returning to cooperation the moment the opponent did. Tit for tat won not because it was clever or unpredictable, but because it was forgiving, transparent, and quick to punish, encouraging long runs of mutual cooperation with well-behaved strategies, while never allowing itself to be repeatedly exploited by aggressive ones. A.K. Joulrod ran a second tournament the following year, publishing new, more sophisticated strategies specifically designed to beat tit for tat. Tit for tat won again. The result reframed how researchers across several fields understood cooperation itself. Rather than requiring central enforcement, laws, or punishment from above, stable, mutually beneficial cooperation can emerge purely from repeated interaction between self-interested parties, as long as encounters repeat often enough that betrayal today can be answered tomorrow. Biologists have since applied the same framework to explain cooperative behavior across the animal kingdom, from reciprocal grooming among primates to mutual defense arrangements among unrelated animals, and economists and political scientists have applied it to everything from trade agreements to arms control treaties. all built on the same underlying insight, A.K. Sulrod's tournament revealed almost by accident. The single-round prisoner's dilemma predicts betrayal is always the smart move. The moment two players meet again and again, remembering what happened last time, the smart move quietly changes into something that looks a great deal more like trust. Should a tolerant, open society extend its tolerance to movements that are explicitly working to destroy tolerance itself? The philosopher Karl Popper raised this question in his 1945 book, The Open Society and Its Enemies, written in the shadow of the rise of fascism in Europe, and he arrived at a conclusion that startled some of his fellow liberal thinkers. Unlimited tolerance, he argued, inevitably leads to the disappearance of tolerance altogether, because a truly unlimited tolerance would have to extend even to the intolerant, granting them the same freedom to organize, to persuade, and eventually to seize power that everyone else enjoys, and once they succeed, they would abolish tolerance for everyone else without hesitation, having never intended to honor the very principle that protected their own rise. Popper's proposed resolution, sometimes called the paradox of tolerance, is that a genuinely tolerant society must reserve the right to refuse tolerance to movements that are explicitly and actively intolerant themselves, not out of hypocrisy, but as a matter of coherent self-preservation, the same way a person committed to nonviolence might still be justified in physically restraining someone actively trying to harm them, without abandoning their broader commitment to nonviolence as a general principle. Popper was careful to note this is not a blank license to suppress any belief someone finds merely disagreeable or offensive. The target of the restriction, in his framing, is specifically the intent and practice of destroying the tolerant system itself through violence or the suppression of others' basic rights, not simply holding unpopular opinions or arguing for unconventional ideas within the normal bounds of open debate. The paradox has become a genuinely difficult, practically loaded question, far beyond its original philosophical context, because the line between merely holding an unpopular opinion and actively working to dismantle a free society is rarely as sharp in practice as it is in Popper's clean philosophical formulation, and reasonable people, all sincerely committed to the same underlying liberal values Popper was defending, frequently disagree about exactly where a specific movement or specific speech falls on that line. Critics worry the principle, once accepted, can be stretched to justify suppressing far more than Popper ever intended. Defenders argue that refusing to draw any line at all is exactly the naive unlimited tolerance Popper warned would eventually dismantle itself. The paradox does not tell anyone exactly where to draw the line. It only insists, against a certain kind of comfortable idealism, that some line has to be drawn somewhere. A casino offers you a simple game. A fair coin is flipped repeatedly until it lands on heads for the first time. If it lands heads on the very first flip, you win $2. If it takes 2 flips to land heads, you win $4. If it takes 3 flips, $8, and the prize keeps doubling for every additional flip needed before the first heads appears, growing without any upper limit at all. How much would you be willing to pay, up front, for a single chance to play this game? The puzzle, first discussed by the mathematician Nicholas Bernoulli in a 1713 letter and later analyzed more fully by his cousin Daniel Bernoulli, produces a genuinely strange result when you calculate its expected value, a standard measure economists and mathematicians use for how much a gamble is worth on average. Each possible outcome, however unlikely, contributes an equal amount, exactly $1, to the total expected value, because the prize doubles exactly as fast as the probability of needing that many flips shrinks, and when you add up infinitely many $1 contributions, one for every possible number of flips, the total expected value of the game is not merely large, it is mathematically infinite. By the standard logic of expected value, a rational player should be willing to pay any finite amount of money, no matter how large, for the chance to play this game even once, since any finite entry fee is smaller than an infinite expected payout. And yet almost nobody, offered the actual game in real life, would pay more than a modest amount for a single play, because the overwhelming majority of actual outcomes are small. Half the time the game ends on the very first flip, paying out only $2, and the truly enormous prizes, the ones responsible for most of that infinite expected value, require dozens or hundreds of consecutive flips to occur, astronomically unlikely events no realistic gambler ever expects to experience. Daniel Bernoulli's resolution, one of the most influential ideas in the entire history of economics, was to argue that people do not actually value money according to its raw numerical amount at all. But according to the diminishing additional satisfaction each extra dollar provides, a concept he called utility, where $100th matters far less to someone than their very first dollar did. Measured in utility rather than raw cash, the infinite expected payout shrinks down to something modest and finite, matching how real people actually behave. The paradox helped found an entire field. You are shown two urns, each filled with 100 colored balls. Urn A contains exactly 50 red balls and 50 black balls, a ratio you are told for certain. Urn B contains some unknown mixture of red and black balls, somewhere between 0 and 100 of each, with no information given about the actual ratio at all. You are asked to bet on drawing a red ball, and you may choose which urn to draw from. Most people, given this choice, pick urn A, the one with the known 50-50 odds, over urn B, the one with completely unknown odds, even though strictly speaking, with no information at all about urn B's actual contents. The rational expected probability of drawing red from it should also be treated as 50%, making the two urns mathematically equivalent bets. The economist Daniel Ellsberg, later famous for a very different reason, leaking the Pentagon Papers, ran experiments demonstrating this exact preference in 1961, and the pattern held up so consistently across different groups of people that it earned its own name: ambiguity aversion, a systematic preference for a known risk over an unknown risk of the exact same calculated probability. The finding created a real problem for classical economic theory, which had assumed that rational decision-makers evaluate choices purely by their expected outcomes, treating an unknown 50-50 chance and a known 50-50 chance as functionally identical bets deserving identical treatment. Ellsberg's experiments showed that real people do not do this. Something about genuine uncertainty about the odds themselves, distinct from ordinary risk where the odds are at least known, feels meaningfully worse to most people than risk alone, even when the numbers on paper come out exactly the same. Economists eventually develop new mathematical frameworks specifically to accommodate this pattern, including approaches that model people as behaving, in ambiguous situations, as though they are pessimistically assuming a close to worst-case ratio might be true, rather than confidently assuming a clean 50-50 split the way the classical theory expected. The paradox reaches well beyond the two urns in the original experiment. It shows up in financial markets, where investors often demand a noticeably higher expected return before they will invest in a genuinely novel, hard-to-assess opportunity compared to a familiar one with an identical calculated risk profile, and in everyday decisions, where the discomfort of simply not knowing the odds turns out to weigh on real choices as heavily as the odds themselves do. Urn B may very well be exactly 50-50 too. Almost nobody wants to bet on it. Can an all-powerful being create a stone so heavy that even that same being cannot lift it? The question, known as the omnipotence paradox, has circulated in various forms through theology and logic for centuries, and it presents what looks like a clean trap, regardless of which way you answer it. If the being can create such a stone, then there exists something the being cannot do, namely lift that particular stone, which means the being is not actually all-powerful after all. But if the being cannot create such a stone in the first place, then there is already something the being cannot do, namely create it, which again means the being is not all-powerful. Either answer appears to disprove the premise the question started with, that the being in question has unlimited power over absolutely everything, seemingly without exception. Philosophers have proposed a few different escape routes, each aimed at a different assumption buried inside the question. One response argues that the paradox rests on a confused, incoherent definition of omnipotence, one that demands a being be able to perform logically self-contradictory tasks, and that true omnipotence should instead be defined as the ability to do anything that is logically possible to do, in which case creating an unliftable stone for an all-powerful being to then fail to lift is simply not a coherent task in the first place, no different in kind from asking whether an all-powerful being can create a four-sided triangle. Another response, associated with the medieval theologian Thomas Ukwy Noose among others, distinguishes between a genuine inability, a real limitation on power, and a mere logical impossibility, arguing that the inability to do something logically incoherent is not really a limitation on power at all, in the same way that a perfectly rational being's inability to believe a contradiction is not evidence that its reasoning is somehow deficient. Some philosophers have taken the puzzle a step further, arguing that omnipotence itself, understood strictly, may be an internally unstable concept the moment it is asked to account for its own limits, since any coherent notion of unlimited power seems to require excluding at least some logically self-defeating tasks from its own definition, right at the point where the definition is supposed to be at its most unlimited. The stone has never been carved in any version of the story, and every attempt to answer the question honestly ends up quietly redefining the very word the question was built to test. Imagine prisoners who have lived their entire lives chained inside a cave, facing a blank wall, unable to turn their heads. Behind them burns a fire, and between the fire and the prisoners' backs, unseen figures walk back and forth carrying objects, casting shadows onto the wall the prisoners face. The prisoners have never seen anything but those shadows, have never seen the fire, the objects, the figures, or each other, and so they naturally take the shadows to be the whole of reality, the only things that exist, giving them names and studying their patterns as if they were the full and final truth of the world. Plato laid out this scene in Book 7 of the Republic, roughly 24 centuries ago, and then asked his readers to imagine one prisoner freed from the chains, turned around, and forced to look directly at the fire and the objects casting the shadows he had spent his entire life mistaking for reality. The philosopher describes this moment as genuinely painful, the freed prisoner's eyes unaccustomed to the fire's brightness, his mind resistant to accepting that the shadows he trusted completely were never anything more than flickering projections of something realer standing just behind him the whole time. Plato pushes the allegory further still. The freed prisoner is then led up out of the cave entirely, into the sunlight above, and the transition is described as even more disorienting than the fire had been, the prisoner initially unable to look directly at anything in the blinding daylight, needing time before he can bear to look first at shadows outside the cave, then at reflections in water, and only eventually at real objects themselves, and last of all, at the sun, which Plato uses to represent the ultimate source of truth and understanding itself. The allegory's final and sharpest turn comes when the freed prisoner, now able to see clearly, returns to the cave to tell the others what he has found. His eyes, adjusted to sunlight, are now poorly suited to the cave's darkness. He stumbles, misjudges the shadows he once read fluently, and the prisoners who never left conclude, watching him fumble, that leaving the cave has only damaged him, and that he should be pitied for what the ascent has done to him. Plato built the whole allegory as a picture of philosophical education itself, of what it actually costs to move from comfortable illusion toward a harder, more genuine understanding of the world, and of how easily that costly clarity gets mistaken, by everyone still comfortable in the dark, for a kind of damage. The shadows are still moving on the wall of every cave in the story, exactly as convincing as they have always been, precisely because nobody inside has any shadow to compare them to. That is 100 small traps, more or less, though anyone counting closely will notice some of them were really the same trap wearing a different coat. A boundary that will not sit still, a self that will not stay in one piece, a rule that undoes itself the moment it is applied strictly enough. Very few of them were ever meant to be solved, in the sense of being closed and shelved. Achilles still catches the tortoise, the cat is still neither one thing nor the other until someone looks, and the ship of Theseus is still sailing under its old name, built entirely of wood that never touched its first ocean. What these puzzles actually do, if you let them, is quieter than solving anything. They loosen a few convictions you never noticed you were holding tightly. That identity is a fixed possession rather than a pattern. That fairness is obvious rather than something that has to be built. That infinity behaves like an ordinary large number. That your own certainty about the room around you right now was ever built on more than trust. None of that loosening asks for a verdict tonight. A thought experiment earns its keep the same way a good question does at a dinner that runs late, not by getting answered, but by changing what the rest of the evening sounds like. Somewhere behind you, if the room is quiet enough, a coin is still deciding whether the shadows on a cave wall count as the whole of reality, and it is in no hurry to land. A donkey is still standing, unbothered, between two identical piles of hay. Neither are you, if you are still here, and there is no reason you should be. That is enough for one long sitting with 100 strange rooms. The traps stay open behind you exactly as you found them, patient, unsolved, and completely undisturbed by having been visited once more tonight. Rest well, or do not, and either way the tortoise will still be there in the morning, exactly as far ahead as it ever was.